Okay, so this is the process. Now let us run through one example and see how we can solve and derive this PM interaction curve. So at this point of time, I would also like to let you know you can do the same thing for parabolic model and an elastic perfectly plastic relationship what you have done in your moment curvature analysis. So that there we can use alpha beta and there the interaction curve very simply. Okay, you can in fact even assume epsilon c equal to 0.003 and you can quickly derive in a conservative way what is your interaction curve, because interaction curve, even if you are slightly underestimating your capacity, it is okay, but only thing is we should not overestimate the capacity. Now in this example we are going to use IS code specified design stress strain curves, okay, not the parabolic one that we talked about in moment curvature analysis. So let us take this section which is having 450 mm by 450 mm cross section, and it is having an effective covered to longitudinal bar as 60 mm. Okay, and I'm assuming that the section is having four numbers of 25 mm diameter bars, and of course I'm not showing the ties. Okay, of course you will have ties also. Okay, and the influence of ties in this axial compression bending is ignored for simplicity. In fact, the tie is going to confine the concrete core. That confinement also we can take into picture, but for simplicity, in fact in your SP16 or any other code also, that confinement is not really considered. But for research purposes, or if you want to estimate the behavior very closely, then you can include that confined stress strain relationship also. So, but anyway, for now, we are not including that or including the confining effect of the ties, which is a reasonably a conservative assumption, right? So, and we have area of bars as 4 into 491, so which is 1964 mm square, and the percentage of steel is, you see here, it is close to 1%. So that is the reason, as I've told you, at least a column should have a minimum of 1%. Okay, so that's why we kept this four numbers of 25 mm bar. Let's see now how to do. So our objective is to derive and draw the PM interaction diagram for this particular section using IS 456 provisions. So let us see. And we can take M40 grade of concrete and FI 500 steel. Okay. And usually columns are cast these days using M30 and above grades of concrete. And okay, so this is the design curve that we are going to follow. So this red color curve, and you know that the maximum stress is 0.447 FCK, and it reaches the value at 0.002, and it can go up to 0.0035. And this strain also, stress when strain is less than 0.02, this is a parabolic curve relationship that we are going to use. When strain is more than 0.002, you are going to take a constant value of 0.447 FCK, right? So for steel, for FI 500, and again we have used the same thing in your calculations for your flexion. We are going to use this design stress strain curve, and the values for this design stress strain curves are given in this table, and FID is given as 0.87 FI. For example, if I'm looking at a strain of not 27, my stress is 413 megapascal for this is valid for FE 500. Similarly, you have the tables for FE 415 also. So in this example, we're using FE 500. So these are the design stress strain curve values. My only thing is up to the stress of 0.8 FID or 347.8 megapascal, I can assume all the stresses to be calculated using linear elastic relationship. If for a given strain, if I multiply by elastic modulus, I'll get stress. Only when the strain becomes more than this value, then more than 0.0017, then I have to use this multilinear relationship to find the strain, right? So now let's look at now. In the interaction curves, we have seen I am calculating at multiple points. I am calculating now pure compression. This is your pure compression, and this is your pure bending, and this is your balanced condition, and this is your E, or when X is equal to D. Now for this case, pure compression, E eccentricity is 0. So for this, let us see how to calculate. So I take this ultimate compressive fiber strain as 0.002. The entire cross section for pure compression, you're going to have the same strain, and you have this kind of strain profile. And as per your IS code, if you see, Pu can be calculated from 0.4 FCK multiplied by the area of concrete plus 0.67 Fi times AC. Okay, so it's not 0.445. Reason is, if in the actual equation we multiplied by zero point 0.9 to end up with this. So this green color is your concrete contribution, and this 0.67 Fi times AAC, area of the compression, area of the steel, is going to be rebar contribution, right? So if you plug in these values, you will find that the total capacity of pure compression capacity of this column as per IS 456 is 3866.5 kilometer. Okay, so and we know from axial behavior, for any given sustained curve also you should be able to calculate uh, the entire load deformation behavior in pure compression, which is straightforward, right? So these are the forces. So you can see here the top steel is in, again everything is in compression. So it is giving 329 and this is giving 329, and concrete is giving 3209. And we have seen that in the axial behavior, in pure compression, concrete is a major load contributor. Steel is going to give you some load resistance, but it's not going to be very high. So you can see here, out of 3,866, only about 660 is given by steel. Remaining 3,200 is given by only concrete. Now let's look at the other extreme, which is a pure bending case. Again, in pure bending case, the eccentricity of compression is going to be at infinity, and that's why it's not going to feel the pure compression at all, but it is going to feel only the bending, which is pure bending case, and your neutral axis is going to be minimum, right? So it is a pure bending. So if you look at this case, then your epsilon cu for failure will become 0.0035, and we have done the iterative calculation. It's a heavily under reinforced section, and you know that in under reinforced section the role of compression steel is not going to be much. So quickly you can find your neutral axis depth, as we have discussed in the first parts of the module. Yeah, I did the iteration and I found XU is equal to 62 millimeter for 62 millimeter, and you will find that the compression steel at the top is going to be at a very small strain, and it's not really going to do much. So from strain distributions, the strain at the bottom is 0.0185. So you can see that again, column sections under pure bending are heavily under reinforced. That means the strain on the tension side is going to be much larger than your yield strain. That is what it is proving here. And then for this strain, if I go back to your design stress strain curve, we are somewhere here, and you get the value of 435 megapascal, which is basically the 0.87 Fy. So if you substitute that, and bottom force is going to be 427 kilonewton. Then now that we got all the forces, so this is in compression. This top, you see that this is giving you only very small force, 22.2 kilonewton, right? And bottom is giving a very large force. So that is why if you add them up, now this is a pure compression. So if I add all the compression and tension, it should go back to zero. That's why if you see 401.8 plus 22.2 should be equal to 427.2. So they are nearly same. Okay. So that is why we say that the equilibrium condition is satisfied. So we get this strain again. We get the strain as 0.003. So we got all these things. So stress is stopped, and this. So you find the forces. So if you sum all of them, Fc works out to be 401.8 kilonewton, 0.36 FCK times B times your XU, and FC plus Fs top is 424 kilonewton, which is nearly same as only 3 kilonewton. So if you slightly increase your neutral axis depth to 62.2 or something, then you will get exact value. But anyway, we can say that the equilibrium condition is satisfied. So now I go back and calculate for this. So if you see here, so you get your force. Let's see this. What are the forces that we are getting? So 427.2. So 62 is, nearly the equilibrium condition is satisfied. So now I'm taking moment about the centroid, right? So now we are talking about pure bending. So pure bending, I can take moment about any axis. So that is the reason I'm taking moment about, let's say, at about this axis. Okay. So say FC multiplied by the lever arm is D minus 0.42 XU, and Fs stop is at a distance of D minus D prime. This is your lever arm for this Fs stop. So if you substitute that, you get the moment resistance of 217.85. Okay, so this XU is actually 62, right? So nearly same. So you get, so we got this point. So what are the points? So if you look at it, so we got PU and this is MU. So we were trying to establish this. First we did this, now we got this. So this is a 217.8 and P is equal to 0. Okay, so this is the value that we got. Now let's go back and assume XU is equal to D. When XU is again equal to D, epsilon C is going to be 0.0035 only. Now you see that the entire section is in compression and neutral axis is equal to depth. So we are trying to find out this point. What is the combinations of axial compression and bending that will produce this strain profile? So again, FC is here, it is straightforward 0.36 FCKBXU. Then I get a value of 2916 kilonewton. Then from strain distribution, bottom strain is working out to be 0.00047, right? It is at a very, very small compressive strain. And for that strain, I get a stress of about 94 megapascal. So then Fs bottom is 94 megapascal. The force is going to be 94 multiplied by 2 into 491, which is the area of steel that get compression of 92.3 kilonewton. Now, what would be the top strain? Again, top strain is 0.00303, 0.00303, somewhere between here, between this and this, 413 and 423. If you do that, you get a value of 421.1 megapascal. Then you can go ahead and calculate force in the steel, top steel as stress multiplied by the area, which is 2 into 491. Then you get a compression force of 413.5 kilonewton. Now we got all the forces. So if you sum all of them, the net force you see here 413.5 compression plus 2916 compression. The bottom is also in compression. So when you add all of them, that is the total compression force that is acting in this cross section. Now, when you do that, you get a total compression force of 3422 kilonewton. Now, when you take moment about the centroidal axis, okay, which is in this case it's a symmetrical cross section, so geometrical centroid and plastic centroid is going to be same. When you take about that, then you get moment Fc times d by 2 multiplied by minus 0.42 xu. So in this case, actually it is not effective depth; it is going to be this capital D. Okay. So this is your capital D because we are taking moment about centroidal axis. So we are taking moment about this axis. Okay. So this is your FC. The distance for this FC and this is going to be this. And so you see if you do that, now you see here. So both of them are adding up. So depending upon 225. So if you do add all of them, then you get a moment resistance of, you see here, this is FC is positive. Let's see if you clockwise. So this is positive lever arm. Now the next fellow is FS bottom. If you see that is, it is taking in negative 92.3 multiplied by 225 minus 60. So that is your, this distance will be negative. Okay, this y will be negative. So that is the reason the moment contribution is negative. Similarly, the next one will be positive. So when you add all of them, you get a moment resistance of 150. So now what are the points that we have got? X value is 158 and P value is 3422. So these are the points that we got. This is your PU and this is your AMU. So that is what it is creating this strain profile. So we got now one more point. First we did pure compression, then we get pure bending. Now we got one more point, combination of PU and MU that creates this strain profile, right? Or in other words, if you assume my XU, I can find out what is the top compressive fiber strain and I can do all the analysis and get PU and MU that produces that strain profile. Now let's go to the XU is equal to XU max, balance condition. For balance condition, quickly we can find because this is also fixed, this is also fixed. Now the XU is going to be within the cross section. So my epsilon CU has to be 0.0035 and epsilon bottom we know it is yielding strain as per the code, which is 0.87 FY by ES plus 0.002. So these strain values are fixed and we know XU max as per your IS code. which is this 177.8. So XU max, I can quickly, using this, I can calculate that. So once your XU max is fixed, then I can find out what are the strain distributions in the top steel and strain distribution in the bottom steel, which you have already found, which is equal to epsilon y. Then you get epsilon is top of compressive strain of 0.00232. And then if you go to the design stress strain curve for 0.00232, you're getting somewhere in between this. So you get a value of 393.85 as per this design stress strain curve. So now that you got the strains, you can get your stresses, and the top is at steel is in compression of 393.85 compression. The force from the compression steel is going to be 393 stress multiplied by the area. So you get a force of 386.8 kilonewton. Similarly, the tension I can calculate, which is 0.00417, and that means that it is a yielding. We know it is a balance condition, so it is going to be epsilon y. So that should give a stress of 0.87 Fy. Then the force is going to be area of steel multiplied by the stress. You get 427.2 kilonewton. So now you got all the forces. Compression force I can calculate because x is within the cross section, 0.36 FCKB times xu. Then I get a force of 1152.4 kilonewton. So when you add all of them, you see here in this case, this is in tension. So this is in compression, the top is in compression, the bottom fellow is in tension. So when you add all of them, this creates a net compression of 1112 kilonewton. Similarly, I can calculate the moment resistance. So you can see here, when you do all of them, you get a moment resistance of 307.6 kilonewton. So again, for balance condition, we got moment of 307.6, comma, axial force of 1112 or something, right? So this is your balance condition. So you got now one more combinations of axial compression bending that creates this kind of strain profile, right? So like that, we got all the 3 points. So this is, what is this? This is your pure compression. This is your pure bending. Okay. This is your balanced condition. This is your when xu is equal to d. So I got only 4 points. So if you write a simple Excel program or a MATLAB program, you can generate all points along the failure interaction curve. Okay. So if you put all of them, you get this kind of thing. So for this particular section, you see here in a simplified way, I did this calculation, I did this calculation, I did this calculation, I did this calculation, and you connect all of them together and you get your PM interaction curve. So this is a curve. So when you do from your analysis, you get your demand. So you will get different demands like this. Okay. So all the demand has to be within this failure curve. Then your section is safe. In fact, it should not be too less also. It should be as close as possible, but within this curve. Then it is an optimum design. Okay. So these are all your demand. Okay. From your analysis have to be kept within this failure curve. Demand from your structural analysis. Okay, so this is your failure curve. Okay, so your demands have to be within this failure capacity curve. Then only your section, what you have chosen, is adequate to resist the stress resultant that are produced from your structural analysis, right? So this is the way we can generate quickly the interaction curve. Okay. Now we can also convert this into non-dimensional form, like what you have it in your SP16. So if PU, if I for any cross section, if I know the distribution of steel, then I can find a non-dimensionalized expression for PU as PU by FCKBD. Similarly, MU can be expressed as MU by FCKBD square. Then I can generate family of curves for different amounts of steel. So that's how the SP16 charts have been derived, right? Right. So with this, we will summarize this lecture. We have discussed about the effect of position of load eccentricity on the column behavior. When your eccentricity is 0, you have pure axial compression. When eccentricity is infinity, you get pure bending. But in practical case scenario, it is going to be some in between these two extreme ranges. and we discussed the salient points in the axial bending interaction curve. We also discussed IS code provisions for how to establish this PM interaction curve. And then we also did one example problem for a 450 mm by 450 mm column and saw using quick calculation of 4 points how we can approximate the or entire interaction behavior. Right. Again, the slides for this part of the video was prepared by one of my MTech student, Mr. Ranjit Kumar. I would like to acknowledge his help. So thank you. So we'll continue in the next parts of the video.